Okay, so we're back at this, and here's another example on delocalization. And here's the question. It says draw the resonance forms for the following and predict which is more stable. So they give us a molecule, and this molecule looks like it has a double bond and a positive charge. So we're probably looking at rule number 1, right? This double bond pi electron moving toward a positive charge. So I know delocalization is going to take place. I mean, the question tells me that, right? But what they really want me to do is tell them which one is going to be more stable when it does delocalize. All right, so let me clear the screen out, and we'll look at the structure that they've given me. So it looks like skeletal structure-wise, this is what's going on with a positive charge right there. So let's show delocalization first. All right, so I'm just going to redraw that molecule. So that way we can show the flip-flop that begins to happen. Well, according to the rules, this particular carbon can take the double bond from the right-hand side and move it to the left-hand side. Well, there was the flip-flop because that pi electron moved toward the positive charge. Well, when that carbon receives those electrons, folks, this positive charge goes away because there's things there now than what wasn't there before. But when this carbon decided to take that double bond and flip it to the left, well, it made that particular carbon lose some electrons. So because it lost some of the electrons, it now becomes a positive charge. So this really are the only two options for the resonance forms. Nothing more than this. The double bond's either going to be on the right-hand side or the left-hand side. And depending on where that location is, that is where the double or the positive charge is going to be, either to the left or to the right. So flip-flop, 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 back and forth. That molecule does it all the time. But is there a preferred version? When this molecule looks at these two options, is one option better than the other? And the answer is yes. Do you know how they make that decision? It's nothing new. We've talked about it. We've talked about it plenty of times. Do you know which version is going to be more stable? Well, folks, to answer this question, take delocalization out. Take delocalization completely out of the discussion and pretend like I give you this question and I say, folks, here are two different structures. Which one of these is more stable? You would look at these, and you did this before. You looked at these two choices and you said, hey, carbocation. Carbocation on this particular carbon is a tertiary position. And carbocation over here, this is a secondary carbocation. So out of the two versions, tertiary is more stable than secondary. So therefore, that particular delocalization form is going to be more preferred. See, I told you. Look at that. It's a blend of everything that we've talked about in the world of delocalization. Once more, it is a cumulative subject. All of those old topics eventually come back in, folks, and here was one of them up front and center. It's the stabilization of a carbocation. And given a delocalization problem, they expected me to go back in the day and talk about alkenes and carbocations and reactions and remember that tertiary is more stable than secondary, which is more stable than primary. The other thing I need to tell you, the more choices, the happier the molecule. Makes molecules very happy. They like variety. It's like the variety pack of chips. You know, sometimes you might get bland and sad and depressed eating the same chip bag over and over and over and over. And the more choices that we give you, the happier that you become. right? I mean, just look at banks and hair salons. I mean, that proves it right there. More choices, the better. Everybody seems to be happy. So that means the more resonance, the more delocalization happens, the happier the molecule as well. So let's take a look at another example problem. It says list the following in order of decreasing delocalization energy. All right, so delocalization energy means it wants to delocalize. All right, which one of these would prefer to be delocalized or prefer delocalization to take place? That's where we have to start. And the question says listed in order of decreasing. So the most delocalization energy to the least delocalization energy. That's how they want me to rank them. So this is what they want me to do. This is what they want me to show that I understand. Delocalization energy, very high delocalization energy, means the molecule is very uncomfortable at this moment. It wants to delocalize so it can get rid of some of that issue that's causing it some disturbance, some depression, some areas where we're kind of treading water here. We have to be really careful. So if I look at these three choices, this one here looks like it's the most problematic. Why? Well, it's got two charges on it. It's got two full-blown negatives on it. If the molecule could rearrange and get rid of some of those negatives, then it would prefer to delocalize, and it would prefer the delocalization to take part. And it can. Look, we have a free set of electrons near a neighbor that has a pi bond. Delocalization can happen here if given a chance. And this molecule, by golly, it's going to delocalize. It's going to delocalize to get rid of some of these full-blown negative charges that are out there on it. Okay, so this is going to be the one with the most delocalization energy. Out of the three choices, this one's going to delocalize first and the quickest because it can get rid of those negatives, and if it can get rid of at least just one, then it's going to. But this whole area, folks, is delocalized because these electrons can actually move in here, and these electrons can be shifted up, and oxygen says, oh no, because look, I can shift them back, and then this carbon says, oh, well, look, we can take some electrons and we can shift them over to that, or vice versa. These oxygens with that pi electron, or the free pair of electrons, can shift them in, and that carbon says, okay, oxygen, you got them now. This whole area can be delocalized. The molecule can fix itself if delocalization happens. All right, so what about the middle one? Well, as you can expect, to the left, we have a charge, and to the right, we don't have any charges. So which one is more prone to delocalize now? Well, it's going to be the molecule to the left-hand side. So the reason, same as before, we have a negative charge. That free pair can be shifted in, and that forces the carbon to shift those electrons up and says, oxygen, you keep them now. You got them. Okay, so that will delocalize, and it will delocalize because it can improve the stability of the molecule by getting rid temporarily of that full-blown negative. It takes that negative charge and it spreads it out really thin like butter on a piece of toast. And then finally, this last example, the least one, folks, it's the one that doesn't have any charges at all, right? I mean, this molecule is kind of very comfortable. There's no reason for it to do anything. I mean, it can. There are free dots there. These dots can move in, and that carbon can move up, and so forth. And a pair of electrons can shift down, which forces that oxygen to get those electrons again. So not a big deal. It can do it, it can delocalize, but it's not as prone to do it as fast. And the reason, no charges. The molecule is very comfortable with what it's in right now. So that's how we would answer a question like this. List the following in order of decreasing delocalization energy. It makes it sound fancy when it doesn't have to be a fancy problem at all. It's just literally looking at molecules and determining which ones would want to rearrange the most. That's all that we have to do with that type of problem. Right now, let's look at this one. Which one has the greater delocalization energy? The one to the left or the one to the right? Okay, well, using what I just told you, let's do that first. I look to the one on the left, and I don't really see any full-blown negatives, do I? Or positives. And I look to the one on the right, and I say, oh, look, there's a negative charge. So if this molecule can delocalize, then this one will probably want to delocalize the most, because it would want to get rid of that full-blown negative. So I would say maybe this one. This one, because this has a negative charge. If the molecule can delocalize, it can spread that negative charge really, really thin through an area of the molecule, and it can improve the stability. And that's what this question's asking, right? Which one has the greater delocalization energy? Which one would be more prone to delocalize? Can they both delocalize, though? Can that actually delocalize, or is this a trick question? Now we see maybe a trick that can happen in some of these problems. Can the molecule to the left really delocalize? Well, let's see. I've got a double bond, and here's a double bond, so pi moves to pi. Can that actually happen? Well, here's my sp2 carbon, and the neighbor next door, guess what, is also an sp2. So yes, these electrons can be shifted in, and these electrons can be shifted there. And vice versa. It can flip around and do the other thing in the other direction. So that can delocalize. Okay, well, what about the one over on the right-hand side? Can that one really delocalize? Well, here we see a free set of electrons, and those free sets of electrons can move toward a double bond as long as it's a neighbor. And folks, in this case it is. That carbon is a double bonded carbon. So these electrons can shift here, creating a double bond. That carbon can say, hey, listen, oxygen, you got to have them. There you go. I'm pushing it up. And we can see a movement of electrons to that molecule. Out of these two choices, folks, that is the one with the greater delocalization energy, because it can take that negative charge and once again spread it very, very thin. Now, let's take a look at this one. Which of the following has the greater delocalization energy? Okay. So with this example, they're very similar. The problem, though, is that in the last two, one had a charge or multiple charges and the others did not. That was a very easy decision to make. Now they give me problem 10. And problem 10 says, which are the greater delocalization energy? And it looks nothing like the previous example problems because there's not charges written on the molecule. But they still want me to look at these two and figure out which one would greater delocalize? More willing to delocalize? How? Well, here's what they want you to do. Has nothing to do with charges. Those were easy ones. If I look at these two examples, this oxygen, folks, can't forget, free sets. Two of them. And over here, same thing. Set here and a set there. And it's my goal to figure out which one of these would prefer to delocalize the quickest. So let's look at the differences here. Here I see a double bond near a double bond, right? So it looks like rule number 2 can actually go forward. Double bond can shift toward a double bond. But it also looks like rule number 3 can happen as well. This is a free set of electrons. The free set of electrons is next door to a double bond, which is next door to another double bond. So I can actually see one shift that happens here, and then this shift that happens there, and then this shift that happens there. Look at that. It's like a chain of reactions that go on. Once the pi bond or pi electrons move toward that pi bond, then a set of chain reactions begin to happen through the molecule. And it really spreads those electrons throughout almost the entirety of the molecule, right? Over on the right-hand side, do we get that? Well, if I look at my free pairs, well, my free pair is not next door neighbor to a double bond or a positive charge or anything like that. So in this particular example, this oxygen with the 2 pairs of electrons, that really doesn't take place in delocalization. It's too far apart. But delocalization can happen. And the reason is because, look, this is a double bond beside of another double bonded carbon. I mean, this carbon's involved in a double bond, and next door we have a carbon involved in a double bond. So we can still get movement that happens here. But when I do that, the problem is that it doesn't happen and it doesn't include that oxygen. So out of these two choices, which one would greater delocalize? Which one would be more willing to delocalize? Which one would delocalize the fastest? That's what this question is after. And the answer is this one. Because there's more areas of delocalization. This molecule can delocalize over a greater area of the molecule. It can stabilize it much better, because if you look at the two, I mean, we pretty much are comparing similar carbons, similar hydrogens, similar oxygens, right? These are not drastically different molecules. So the one to the left would have greater delocalization energy because delocalization happens in more places. That is what problem 10 is about. Now, with that, we need to venture on to the next topic of delocalization. And that is this thing called a diene. Do you remember what dienes were? Way back in that lecture module of alkenes. I told you, it's all coming back. A diene is 2 double bonds. So carbon double bond carbon to maybe, oh, I see. We were talking about dienes back in the day. I'm dying to know. And we named them. We did some reactions with them, maybe, right? But we at least named them. But now we need to bring them back into the conversation, because look at what happened here. I did a double, single, double. That's a delocalized network. A pi bond can move toward a pi bond in this template of a diene. So in the next video, we're going to pick up the discussion with dienes. And we're going to classify different types of dienes, and we're going to take another look at them. And now what we're focused on is the delocalization that can happen with some of the dienes that we might see in these reactions. So stay tuned. Come back. We're going to dig out an old topic, and we're going to freshen it up, and we're going to make it new with a pretty little bow. I'll see you then.